We're continuing in Rosen Discrete Mathematics and its Applications, section 1.6 on rules of inference. And we will now discuss how we handle quantified statements. We've been discussing how to handle propositional logic, and now we'll use the quantified statements with predicate logic and propositional functions. So we will be able to combine those to to make arguments for more complicated situations. All right, so the next rule of inference is called universal instantiation. Above the line we have for every x, p of x. And from that we can conclude that p of c is true for any c in the domain. So here our domain is all dogs and Fido is a dog. All dogs are cuddly is our premise, and therefore we can say that Fido is cuddly. That's universal instantiation. Universal generalization. If we say that P of C is true for an arbitrary C in the domain, that means it is true for every element in the domain. So P of C for arbitrary C means we can conclude that for every x, P of x. Sometimes that last step is not made, and so in some math proofs, well, it'll be skipped, but that's called universal generalization. It might be useful for getting to a requested conclusion. All right, so now we have existential instantiation. So the premise is for every, there exists x, P of x. And from that we can conclude that P of C is true for some element C. For example, there is someone who got an A in the course. Let's call her lowercase a and say that lowercase a got an A. So as long as we're clear about what C is or what A is in the instantiation, the instance of our interest, as long as we're clear that it's in the true set for P of x. And then there's existential generalization. If P of C is true for some element C, then we can conclude that there exists x P of x. Michelle got an A in the class, therefore someone got an A in the class is the conclusion. So universal instantiation, universal generalization, existential instantiation, and existential generalization are the quantifier-based rules of inference. All right, so let's use them in an example. Here we have the conclusion we want to reach is John Smith has 2 legs, and we have 2 premises. Every man has 2 legs, and John Smith is a man. So we have to designate some propositional function. M of x is a man, L of x is x has 2 legs. And we are going to say that John Smith comes from a member of the domain. All right, so let's take a look. I don't have a build here, so we'll just start at the top. We have the premise for every x, m of x implies L of x. That is, every man has 2 legs. And we're going to do universal instantiation from 1. Since every man, since this premise is true for every man, it'll be true for John Smith. So we can say MJ implies L of J. And now we have another premise. We've justified 1, justified 2. Now we have another premise that J is a man. Man at J is true. So we can write that down as a premise. And then because we have an implication as a thing we know in 2, and its hypothesis is that we know is true in 3, we can use modus ponens on 2 and 3 to say L at J is true, or that J, that John Smith has 2 legs. And this should look very familiar to you. This is exactly the same structure that the Socrates argument will take. Okay, so let's look at another one. We have a conclusion that someone has passed the first exam who has not read the book. We want to show that it follows from these premises. A student in the class has not read the book, and everyone in the class passed the first exam. First of all, we need to look for quantification language. Someone suggests there exists, a student suggests there exists, and everyone suggests for all. And then this would be some kind of conjunction. Pass exam, did not read the book. Right there. A student in this class has not read the book. Straightforward negation of a proposition. And everyone in the class passed the first exam. Okay, so we can create some propositional functions for these. C of x is in the class. B of x is x has read the book. P of x is x passed the first exam. And x, we would say, comes from the domain of people. All right, so here we can write down the premises. That third premise goes, I mean, that first premise goes in the first line. It's there exists x, c of x, and negation of b of x. And the second premise is on the second line. For all x, c of x implies p of x. Okay, so everyone in this class has passed the exam. If you're in the class, you have passed the exam. So that's implication language. And then we're going to conclude or want to show that there exists x, p of x, and not b of x. In other words, somebody in the class passed the first exam and did not read the book. All right, and we will run through this argument on the next page. And as is typical, we start with a premise. And we'll start with there existing a person in the class that has not read the book. And the first step will be to use existential instantiation to break that down to a specific person, and we'll call it A. So this is existential instantiation from the first line, which is a premise. All right, so C of A and not B of A, we'll use simplification to pull out C of A. And that means A is in the class. And now we'll take the next premise for every x. C of x implies P of x. And what does that mean? We can use universal instantiation to say that C of A implies P of A, since it applies to every person in the domain, including A. So all of these A's are the same person. We don't know who it is, but it's the same person. And now we have in 3 and 5, it looks like we can do modus ponens to conclude P of A. So we have the implication and we have affirmed the hypothesis, so we can conclude P of A. That means A passed the exam. And we want, remember what we're trying to conclude is that somebody's passed the exam and not read the book. So we're going to grab the negation of B using simplification from line 2, right there. And now with 6 and 7, we have the two things we want concluded that they're true. We want to combine them using conjunction. So we'll conjoin 6 and 7 to get line 8, P of A and not B of A. And remember, what we wanted to conclude is that there exists X such that P of X and not B of X. But we can do that since we found a person. This is true for A. So using existential generalization, we can now write there exists X such that P of X and not B of X from line 8. And that's using the rules of inference for quantification and propositional functions combined with the rules of inference that we saw for propositional logic earlier.